This video is a continuation of topic 18, where we're solving quadratics given in vertex form using the square root method. As always, when we're solving quadratic functions, we're looking for x values that make the equation equal to 0. As we find these answers, or zeros or roots, sometimes we get values that are not x-intercepts, but are still answers, roots, zeros, solutions nonetheless. These solutions involve imaginary or lateral numbers. To help us understand this a little bit more, we're going to go ahead and use another video source. This video comes from the Welch Lab, creating math and science videos. Specifically, we're going to use their first video, Imaginary Numbers Are Real, Part 1 and Introduction.
Let's say we're given the function f of x is equal to x squared plus 1. We can graph our function and get a nice parabola. Now, let's say we want to figure out where the equation equals 0. We want to find the roots. On our plot, this should be where the function crosses the x-axis. As we can see, our parabola actually never crosses the x-axis. So according to our plot, there are no solutions to the equation x squared plus 1 is equal to 0. But there's a small problem. A little over 200 years ago, a smart guy named Gauss proved that every polynomial equation of degree n has exactly n roots. Our polynomial has a highest power, or degree, of 2, so we should have 2 roots. And Gauss's discovery is not just some random rule. Today we call it the fundamental theorem of algebra. So our plot seems to disagree with something so important, it's called the fundamental theorem of algebra, which might be a problem. What Gauss is telling us here is that there are 2 perfectly good values of x that we could plug into our function and get 0 out. Where could these 2 missing roots be? The short answer here is that we don't have enough numbers. We typically think of numbers existing on a one-dimensional continuum, the number line. All our friends are here. 0, 1, negative numbers, fractions, and even irrational numbers like root 2 show up. But this system is incomplete. And our missing numbers are not just further left or right, they live in a whole new dimension. Algebraically, this new dimension has everything to do with a problem that was considered impossible for over 2,000 years, the square root of -1. When we include this missing dimension in our analysis, our parabola gets way more interesting. Now that our input numbers are in their full 2-dimensional form, we can see how our function x squared plus 1 really behaves. Our function does cross the x-axis. We were just looking in the wrong dimension.
This idea of a parabola being 2-dimensional and finding our answer in some other location other than the xy coordinate plane is kind of mind-blowing. However, if we think back to what the original problem was and why we have this other dimension, we think back to our original problem, which was finding a number that when we multiply by itself, it yields a negative number. It's fine with positives. 3 times 3 gives us positive 9. Negative 3 times negative 3 gives us positive 9. But what value can I multiply by itself to give me a negative answer? We have this issue. We can see this a little bit more clearly if we use arrows to help us as we look at our multiplication. So if I took a positive 3 and multiplied it by another positive 3, we end up with an answer of positive 9, firmly over in positive territory. However, if I start with a negative value of -3 and I multiply it by a -3, what this does is it results in a 180-degree rotation, and our answer ends up being firmly in the positive area, which we know is positive 9. We see that this 180-degree rotation occurs when we just multiply a positive and a negative value. So if I start at positive 3, and let's say I multiply it by -2, well, that puts my answer down in the negative territory at -6. These aren't the same value, but again, we're noting that we have this 180-degree rotation happening when I multiply by a negative. So there's no way for me to go ahead and actually end up in my negative region like we want for this -9. So it kind of begs the question that, man, it'd be really, really nice if there was some type of number that would only rotate my values 90 degrees. So that way, when I multiply by that number again, I rotate another 90 and end up firmly in my -9 territory. This is exactly what an imaginary number does. Rotating 90 degrees, then rotating another 90 degrees when I multiply by that same value, allowing us to go ahead and get an answer that is actually negative. So we have this new number. The question is, though, how can I put this together with our traditional XY coordinate plane? How do they coexist? So if we view our traditional XY coordinate plane as a flat piece of paper, we can take our imaginary values, right? So we have our XY coordinate plane as a flat piece of paper. We can take this idea of the imaginary values and we can lay them perpendicular to it, coming directly out of the x-axis, directly off of our paper. So looking at those two values together, we kind of get this meshing of the idea of two perpendicular planes that intersect at the x-axis, where we have, again, our imaginary values coming directly out and behind our sheet of paper, if you will, directly perpendicular to it, from our traditional XY coordinate plane, which we would imagine being flat. So this imaginary number idea allows us to perform that 90-degree rotation, but instead of going up or down as we would if we were on a flat sheet of paper, we actually rotate out or behind in order to give us that 90 degrees. And then when we rotate again, we end up back on our flat sheet of paper. So we're using this two-dimensional idea to help us jump over and find a negative value. Well, all this theory is great, but you're probably wondering, how does this help us solve our problems? We have this method of solving by square roots, which we used in the previous section. Identify to make sure it's in vertex form, isolate our something squared, take the square root of both sides, and solve for x. How does that apply to problems where I don't actually get the x-axis? I have an x-intercept. Does it change it? The answer is no. We can go about solving this problem, x plus 2 squared plus 1 equal to 0, exactly the same way. I can start off by subtracting 1 from both sides, which isolated our something squared. So now I can take the square root of both sides, which undoes the squaring on one side, leaving us with x plus 2 is equal to plus or minus the square root of negative 1. Now, we dealt with square roots last time. This time, though, we have the square root of negative 1 to deal with, which we know to be an answer of just 1i. So here's where our imaginary values come into play, and we have x plus 2 is equal to plus or minus 1i. To isolate for x here, we'll subtract 2 from both sides, giving us x is equal to, now at this point, negative 2 plus or minus 1i, this doesn't seem possible. We can't add an imaginary number and a real number together. So just like before when we had 2 plus or minus root 3, we will just leave our answer as 2 plus or minus 1i. Will give us our final answer that we're looking for. And there it is. We solved this algebraically, and we got our answer of an imaginary or complex number. Now, what this looks like, if we were actually to graph it, is this picture down here. What's actually happening is we're taking this quadratic, this parabola, we're reflecting it down with the negative, and we're rotating it 90 degrees, which was the idea of that I, so that way our answer shows up in this perpendicular plane of the imaginaries, this perpendicular plane that coexists right with the real numbers. It just comes straight out and behind of our sheet of paper. Well, I'm not going to ask you to graph this imaginary two-dimensional plane every single time. However, we do have a trick to help us visualize what's actually happening on a one-dimensional plane. So what we can do to kind of help us see the answers, quote unquote, is we can start by reflecting our quadratic. So this is the same quadratic. We can take and reflect this quadratic down. So here I'm going to go ahead and go over 1 and down 1 in this case. And as I draw my quadratic, we've now reflected this down. There is, in fact, the negative that we've done. Now, this answer that we got, 2 plus or minus 1i, the 2 portion of our answer, so this would be the 2 portion of our answer, or which is the real value, is just here a value of 2. It's just the center of our graph or our axis of symmetry. The imaginary portion of our answer, in this case the bi, so in this case it's 1i, that 1 is represented not on the x-axis, but it's actually just the distance from the middle of my graph to the x-intercept that we've just generated. So from negative 2 to negative 1 is a distance of 1, and from here, from negative 2 to negative 3 is a distance of negative 1. That's that idea of me moving that imaginary. If I were to reflect it down from negative 2, I would go plus 1 and negative 1 in each direction to get my new x-intercept. Okay, so it's kind of a visual check of what the answer of 2 plus or minus 1i would look like if I were to actually go ahead and rotate it 90 degrees, which, again, we're not actually able to do on this flat surface. So let's take a look at another example, kind of using this idea. Let's look at the graphical approach here. Let's actually see what the answer looks like. Here is my quadratic negative 1/2 x minus 3 squared minus 2 is equal to 0. We're going to go ahead and we're going to reflect this up. So I'm going to grab some points and reflect them up. And we see right here and right there is my quadratic. Now, in terms of my answer, if I was doing this, my real portion would be 3. So my answer is going to be x is equal to 3 plus or minus. Now, I can visualize the imaginary portion as how far it is from the center of my graph to the x-intercepts that we've now generated with this reflection. We could see that this is a positive 2 move and this is a negative 2 move. Again, the idea being that this is an imaginary. So my answer should be x is equal to 3 plus or minus 2i. X is equal to plus or minus 3 plus or minus 2i. Well, let's actually go ahead and do the algebra and check this out. We're going to go ahead, this is vertex form. We're going to start by isolating to something. Start by adding 2 to both sides. We're then going to multiply both sides by negative 2, giving us x minus 3 squared is equal to negative 4. We can now go ahead and take the plus or minus square root of both sides. The plus or minus square root undoes the squaring on this side. X minus 3 is equal to plus or minus the square root of negative 4. Now, the negative means that we're going to have some I in our answer, and the square root of 4 we should know by now is equal to 2. So we get x minus 3 is equal to plus or minus 2i. I can add 3 to both sides, giving us an answer of x is equal to 3 plus or minus 2i. The exact same answer I got when I helped visualize via my graph reflection and our distance from the axis of symmetry of 3. Now, we don't always need to do this. Sometimes it's not even really possible because we get our answers that aren't nice values, which is what's going to happen here in our next example. I would like to make note that this is technically in vertex form. If we were to start by setting this equation, making this equation say equal to 0, we would add 13 to both sides. And yes, we would check this is in fact in vertex form. However, we don't really want to do that because we're trying to isolate for x in this case. Just a nice mental check for us to know that this actually is what we're looking for. So, and we can use the square root method. So let's go ahead and start solving them. Subtracting 7 from both sides, taking the plus or minus square root from both sides here, gives us x plus 4 is equal to plus or minus the square root of negative 20. Simplifying the square root of negative 20 gives us a value of 2i root 5. Notice again our imaginary comes up because of the square root of the negative 1 underneath. So finally simplifying this, we're going to subtract 4 from both sides, giving us x is equal to negative 4 plus or minus 2i root 5. No way we can actually add those together. That's too crazy of an answer, so we're just simply going to leave it there. Now, that's about as crazy as it's going to get in terms of the problems that we're going to be expecting of you. Go ahead and jump back into the notes and go ahead and try questions 5, 6, 7, 8, and then a little bit of review on questions 9, 10, and 11 on the bottom. So questions 5, 6, 7, and 8, the key is posted online and also visible here. Go and give these a try.